Welcome to the deep dive. Today, we're tackling a really fundamental, almost mind-bending topic from physics.
Absolutely. We're looking at the inside of black holes,
Yeah.
specifically the chaos near the singularity.
Right, the singularity. And this has real relevance, I understand, particularly for, say, UPSC aspirants trying to grasp core physics concepts.
Exactly. It touches on gravity, space-time, quantum mechanics, the big questions. We're drawing on recent theoretical work, highlighted in places like the Munich Eye.
Okay, so the singularity,
Hmm.
this point of what? Infinite density, where
Yeah.
everything we think we know about physics just stops.
Pretty much, yeah. It's where general relativity and quantum mechanics clash. Our mission today is to unpack recent ideas about how chaotic things get in there.
Chaos inside a black hole sounds intense. Is this a new idea?
Not entirely new, no. Back in the 1960s, Charles Misner came up with the Mixmaster universe concept.
Mixmaster, like a kitchen gadget.
Sort of, yeah. The analogy was space-time near the singularity getting violently churned, stretched in some directions, squeezed in others, completely unpredictably.
Wow. And didn't Kip Thorne have that vivid description of an astronaut?
He did, being essentially spaghettified and, well, dismembered by the tidal forces and chaotic stretching. It paints a picture.
A grim one. But actually studying this mathematically, that must be incredibly hard.
Oh, absolutely. Einstein's theory of general relativity, which describes black holes, involves these really complex field equations.
How complex are we talking?
Well, there's 16 interrelated equations. You change one part, and it ripples through everything else. Hugely difficult to solve, especially for something as dynamic as a singularity.
So Misner tried to simplify them back then.
He did, with approximations. But those methods had limitations and were eventually, put aside. It created a kind of gap in the research for a while.
But now people are jumping back in with new tools.
Exactly. There's renewed interest using more powerful mathematical techniques to revisit those early ideas, check the approximations, and importantly, try to connect general relativity with quantum mechanics.
Okay, so what changed? You mentioned work from the late 60s.
Right. A big shift came with the BKL solution. That's Belinsky, Kalatnikov, and Lifshitz.
BKL, got it. What did they find?
Well, before them, simplified models often assumed black holes formed perfectly symmetrically.
Hmm.
BKL looked at more realistic scenarios, like formation from irregular collapsing objects.
And that makes a difference.
A huge difference. They found it leads to a wildly turbulent environment near the singularity. Instead of smooth space-time, you get these violent oscillations, dimensions fluctuating, chaos.
So that's where the chaos idea really gained traction, and it highlights the core problem, right? The clash between smooth space-time and relativity and the quantum world.
Precisely. Relativity assumes space-time is continuous, but quantum mechanics introduces the Planck length, a scale below which distance itself becomes sort of meaningless.
How do those two reconcile at a singularity?
That's the billion-dollar question. The BKL group argued that the intense gravity near the singularity could essentially decouple tiny regions of space.
Decouple, like cut them off from each other.
Yeah, so these minute segments of space could start operating independently, behaving chaotically. It makes the maths even more complicated. Current research is trying to figure out exactly when and how this chaos turns on.
And I read something about the ATA-CFT correspondence helping here. Sounds complicated.
It is quite advanced, yes.
Right.
Developed by Juan Maldacena, think of it like a mathematical dictionary. It relates theories in different numbers of space-time dimensions.
A dictionary between dimensions. How does that help with black holes?
It allows physicists to study certain aspects of black holes, which exist in our familiar dimensions, by looking at a mathematically equivalent, often simpler system in a different dimensional setup.
Okay, so using this ATA-CFT dictionary.
They found chaotic behavior in the other dimension system that strongly mirrors the kind of chaos predicted by BKL back in the 60s for our dimensions. It's a powerful piece of evidence.
Wow. So where's this research heading now? What are the latest insights?
People are working hard to refine the models of these unpredictable oscillations inside black holes. There's even some fascinating, though speculative work suggesting structures called modular forms.
Modular forms? What are those?
There are complex mathematical functions with deep symmetries. Yeah. The idea is they might somehow capture the patterns hidden within the chaos near the singularity.
Patterns in the chaos. That could be huge.
It could be. If it pans out, it might give us clues about the fundamental structure of gravity itself, maybe even point towards a theory of quantum gravity.
It's amazing we can't actually see inside a black hole because of the event horizon.
Correct. Direct observation is impossible.
But these theoretical frameworks, these mathematical tools, are letting us probe the physics in these extreme environments anyway.
That's the power of theoretical physics. It pushes us to understand the universe's fundamental rules, even in places we can't directly look.
So wrapping this up, especially for our listeners maybe studying for UPSC or just fascinated by physics, the big takeaway is that inside black holes, near that central singularity, space-time isn't smooth or predictable. It's thought to be profoundly chaotic.
A realm where our current physics breaks down and something new, likely involving quantum gravity, takes over. It really challenges everything.
Which leads to a final thought to leave everyone with. If there's such extreme chaos at the heart of these massive objects, what might understanding that chaos tell us about order and structure elsewhere in the universe?
An intriguing question, definitely. How does structure emerge from such fundamental unpredictability?
Food for thought. If you found this deep dive useful, perhaps for your UPSC prep, or if it just sparked your curiosity, please do like, subscribe, and let us know any questions in the comments. For more details, check out the source article in the Munich Eye.
Thanks for tuning in.
Until the next deep dive, keep questioning.